Hello everyone! Anette and me will show you a tool that powered many recent developments at ParityQC and will probably enable many more.
We have developed a formalism called the flow formalism to intuitively track how quantum information spreads in quantum circuits. This has proven very useful, for example, in the construction of efficient quantum circuits when decomposing to CNOT gates and single-body rotations. But let's start in the beginning. We know that Cliffords map Pauli operators to Pauli operators, therefore also Pauli eigenstates to Pauli eigenstates. In particular, if we look at the CNOT, it actually maps Z eigenstates to Z eigenstates. So why not track a circuit of CNOT gates by its effect on these Z eigenstates? So let's look at the easiest circuit with just a single CNOT gate in it. Now, what does a CNOT gate do? On the Z eigenstates, it writes the parity of the control and target onto the target qubit. So if we just denote the two qubits we have with some variables for the eigenstates, after the CNOT gate, the second qubit, where the target of the CNOT was, is now encoding the parity of the two original eigenstates. Now we want to somehow label that in our circuit. So we just denote some label 1 and 2 for these two eigenstates. And after the CNOT, we simply write 1 and 1 to here to denote that here now we have encoded the parity of the two variables S1 and S2. Now you can do this also for larger CNOT circuits, of course. So let's start with this one. We have 3 qubits, we label them 1, 2, 3. And we do the same thing. This CNOT now imprints the parity 2, 3 on this qubit here. The next CNOT imprints the parity 1, 2 here. Now we have something a bit more interesting happening. Now we have the parity of 1, 2 and 2, 3. But of course, this is all spin variables, so like if we have the same variable twice, it just cancels out. So we get just the parity 1, 3 here. And we go on like this. Now this CNOT gate imprints 1 onto the 1, 3, so we end up with 3. And 1 onto the parity 1, 2, we end up with 2 here. And this is already nice. We have just labeled the circuit now with this rule. And what we see now is this actually implements the identity, because whatever eigenstates we were here in the beginning, we are in exactly the same eigenstates in the end. And even if I have superposition of these eigenstates, the same thing counts. So just by labeling the circuits, we have found out that this is the identity. I haven't had to write any matrices, any vectors, or any math. So this is a really easy tool even to already prove some circuit identities or check some relations between CNOT circuits. Okay, let's look at the whole thing in the X spaces. So before I said CNOTs map Z eigenstates to Z eigenstates, but in fact they also map X eigenstates to X eigenstates. So if I start with my 2 qubits in some kind of X eigenstates, denoted by this variable t, then what the CNOT does is it actually imprints the parity of these 2 eigenstates now on the control qubit and not the target. And we can also put that as a label into our circuit. So we'll use a different color now. We use these 2 new labels, blue just to distinguish from the red labels, and also we put them in bracket to make it easier to distinguish without colors. And now if we follow this rule, what we have to do is we just have to write this 1, 2 label now on the control qubit, and the 2 stays the same on the target.
So after we've seen what the CNOT does to the eigenstates, we can reinterpret it as the action of the CNOT on the Pauli group again. And we see our labels on the left-hand side CNOT, and we can say, okay, what's happening to a Pauli, which is after the CNOT, when we want to pull it into the front of the circuit. And this is what the map does here from the Pauli group to the Pauli group, and the X1 after the CNOT maps to an X1, X2 before the CNOT. And this is exactly what we are labeling the circuit for. And we can do this, of course, for all the generators of the Pauli group. But if you look closely, then you'll see that that is naturally iterative in the backwards direction, because we can put a Pauli in the end of the circuit, can pull it back through the second CNOT, then pull it back to the first CNOT, and then get the equivalent operation in the beginning of the circuit. But what Anette already showed is that we have it iteratively in the forwards direction, and this is possible because we are tracking actually a symplectic basis. Or to put it differently, we track all the generators of the Pauli group, and they have the normal anti-commutativity rules we are accustomed to, and then we can look what's happening if we are concatenating the 2 circuits. On the first wire, we just replace all the labels coming on the first wire by the labels of the first circuit, and on the second wire we do exactly the same, and of course simplify parities where they come on. And this is really due to the fact that actually what we are doing here is a symplectic automorphism of the symplectic vector space, as already seen in Clifford tableaus, but here in the backwards direction.
So let's try this whole labeling out on a first example to see really how we can understand quantum circuits this way. And a really intuitive example is quantum state teleportation, which usually takes a lot of math to actually explain and understand why this is working. But you can in fact understand everything that's going on just by looking at these labels. This is the general circuit for quantum state teleportation. We have our input qubit here, which is a completely unknown state, so we just give it some x and some z label. And we have two ancilla qubits down here. The first one is initialized in the state plus, so I already know which x eigenstate this qubit is in, so I don't really have to give it an x label, because I know this state. At the same time, I know that the z eigenstate of this qubit is completely random, because this is a maximum uncertainty state in the z basis. So I give it some label, but I really keep in mind that this label does not represent any actual quantum information. It is really a placeholder for a fully random variable. And the same I can do with the second ancilla qubit. This one is in the zero state, meaning I know exactly which z eigenstate this qubit is in. So I don't give it a z label, but I give it some kind of placeholder x label to denote that there is some fully random variable here. Now, let's look what's going on with this first CNOT. We just follow the usual rules. So on this basis, the A moves down and it gets added to this empty label. So now we just have an A here, and the same happens with this B moving up. And this is actually a Bell state. And this is a really nice way of looking at a Bell state, because what do we see? We see that no matter which basis we measure any of these qubits, we will get a completely random output. But if I measure both of the qubits in the same basis, for example, both of them in the Z basis, they will have exactly the same measurement outcome. And this is exactly the characteristic of such a Bell state, that there is no real information here, whatever I measure is random, but there's correlation between these qubits, which I see exactly in the fact that they both have the same labels. Let's go on and see the actual teleportation circuit. So first of all, we have the CNOT now entangling our Bell state with our input qubit. We follow the same rules again, so this is the new labels we get here. And then we measure. And the first measurement is a Z measurement of our original qubit. Now, the first question many people might ask is like, if I measure this qubit, I get information that I don't want to obtain of my quantum state. But what we see is we measure in the Z basis. So we measure the value of this variable, which is the Z1 value, relatively to this completely random value A. So all I get is what's the state of qubit 1 relative to the state of a completely random unknown quantum state. So this actually doesn't give me any information, at least no useful information about the state that I want to teleport. So let's go on. What do we do now? We do some bit flip on this qubit depending on the measurement outcome. Meaning, depending on whatever this state was that I measured, this value, I'm flipping this bottom qubit state, which in labels I can actually just represent by adding this label that I measured to the label that I already had here. And then again, I can do some cancellations. This random value cancels out. And in fact, now I have the actual quantum value, or the value of this quantum state Z1 on my qubit without ever having actually obtained the exact value. And I do the same now with the other qubit. I do an X measurement here, which gives me the value of X1 relatively to this random variable B. And I do another flip. Now I do a Z flip, so I change exactly the other eigenstate. I change the X eigenstate, depending on what I measured here. I cancel out the B, and ta-da, I've got my completely unknown quantum state psi on this qubit here without ever having obtained any information about it and without having physically moved this qubit down here.
So after this example of the teleportation, we can also look at single qubit rotations, because the labels show us what's happening to the Pauli operators. They also show us what's happening to the Pauli rotations, actually. So in this example here, we have the single qubit rotation RZ, and the only thing we have to do is look at the label down here. It's a 1, 2, red, so it's Z. And we see, okay, this is just a Z1, Z2 rotation. And we can actually do this for any Clifford circuit we could think of, just by putting in the single qubit rotation in the space we want to have it, read off the label which we have there, interpret it as written down here, and then we see, okay, this is the rotation we have implemented in this circuit. And this simple way of interpreting rotations is very helpful in synthesizing circuits. Some of the most impressive outcomes of these labeling methods are our circuits for the quantum Fourier transform, as well as for the quantum binary optimization problems on a linear chip layout, beating all known previous versions in gate count and depth. And they were found by using the labels to track the encoding of the different many-body terms. We start by implementing a Clifford circuit which produces the labels of some first set of needed rotations. And the trick is then to embrace the code deformation introduced by this circuit and move on from there to the next set of useful labels. With the help of the labeling, we were then even able to generalize this to implementations on different hardware connectivities, finding improvements on all scenarios.
So let's generalize this whole thing to the full Clifford group, because in fact, as we know, every Clifford gate maps Paulis to Paulis. So let's try to actually also adapt our labeling to the full Clifford group. First thing we can look at is the Hadamard gate. What does the Hadamard do? It maps X operators to Z and Z operators to X operators. And in terms of labeling, we can actually easily do this by just taking whatever was down here and writing it up, and whatever was up here and writing it on the bottom. The next gate is a bit more interesting, which is the S gate. Maps the X operator to a minus Y operator and leaves a Z operator unchanged. So how do we do this with labels? Well, whatever was here on the Z operator, we just leave unchanged. And whatever was the X operator gets multiplied by the Z operator, because we don't really have variables to denote Y, but we can always represent Y as a product of X and Z operators. So this is then the way we can actually shorthand write the minus Y operator as minus I times X1 times Z1. And now, last but not least, an actually relatively simple case, if we have an actual Pauli operator, like for example the Z operator here, all it does, it gives us a phase -1 in front of the X operator, so we literally just write a -1 here. Keep in mind that this minus is not really a phase in front of a quantum state, but what we're denoting here is really shorthand notations of eigenstates. So this is a minus in front of the eigenstate, meaning I'm just swapping which eigenstate I'm in. If I was in one of the two eigenstates before, with this minus, this is the other eigenstate. In the most general way, then this is how it looks like. We have some kind of Clifford circuit, and after this Clifford circuit, we can write new labels, and on top of each qubit line, we can then write the label which transforms whichever label was written here before, which in the initial setting of a qubit, usually we choose the X operator here, and similarly on the Z label, we could write the transformed label of a Z operator. The next thing one can actually incorporate into this formalism is measurements. Now, we've already seen this in an example before. So what happens if I measure some operator? In this case, if I measure the X operator of this qubit, I obtain some information about whatever variable, whatever quantum state I have represented here on the top of the qubit line. In this case, it was just some ancilla variable A. Now, this measurement outcome, it tells me now information about this random variable A. Depending on if I measured this in plus or minus 1, I could in principle now substitute this variable A by plus or minus 1. For example, like in this case. So now instead of 1A, I can just write plus minus 1 and forget about the A because I have measured that. Now this is not looking so great because now the outcoming state here is actually depending on the measurement. So this is not really a deterministic quantum circuit anymore, because I don't really know which state I will end up in, because it depends on whatever I measured up here. This is why often measurements are also accompanied by by flips depending on the measurement outcome. And in this case, you can make the circuit deterministic again by doing a Z flip here whenever I measured -1 up here. Because what does that do? The Z flip changes the X eigenvalue. So if I measured -1, I'll add another minus to this variable here, meaning in the end, I actually cancel out whichever this was. If it was a plus, nothing happens. If it was a minus, I added another minus, and I actually end up with exactly just the state x1 or z1 here without any reliance on the measurement outcome. And in this case, I could actually also take a little shortcut and just say directly, I measured this variable and I do a depending z flip depending on the measurement outcome. So I just take this variable here and I plug it onto the x label here, and then the a cancels out. And again, I directly see that in the end I have my quantum state, which is just x1 on z1, and I have completely removed this other variable a. Let's try and use this formalism to actually do a little bit more even, which is labeling stabilizer codes. We can do this in exactly the same way as we labeled quantum circuits if we just look at the encoding circuit of our stabilizer code. So here we have a really simple example. We have 2 qubits with some information on them. For now, I'm just writing the Z labels. And we have added 1 ancilla qubit in the state 0. As already said before, this is in the state 0, so I don't really have to give it any Z label because I know which Z eigenstate this qubit is in. Let's add some kind of encoding circuit like this, for example. We get 3 labels in the end here. We get a label Z1, Z2, but at the same time, on another qubit, we also get a label Z1, Z2 here. So this is actually nice because now we have these 3 different operations. We could do an RZ1 here, RZ2 here, and an RZZ1, 2 on this qubit at the same time because we're using the redundancy of the encoding. So this is already a nice thing. It can be really useful for parallelization of many operations. I was talking about stabilizer codes, so let's actually see how this is a stabilizer code. And we see this if we also look at the X bases. So of course our input qubits also just have their own X label. The ancilla now also needs to get an X label. As mentioned before, this is exactly this completely random variable because I know this is in a Z eigenstate. So the X value of this qubit is completely undetermined, and I need to somehow denote this by adding a variable. If we're looking at this in terms of operators and not eigenstates, this is the X operator on this qubit 0, and I have assumed before that this qubit stays in the state 0, and I want to use this as a stabilizer for my stabilizer code. But of course, this assumption is only true as long as I don't do an X flip on this qubit. So in fact, I will now interpret this operator A as the forbidden operator in such a stabilizer code, because whenever I would do an operation on this value, on this operator, this would exactly flip this qubit's value, but I wanted this qubit to be in this certain stabilized value. So now if I move this A variable through the circuit, in the end I see that actually each of the qubit ends up with an A in their X label. And this actually tells me that any of these qubits, I am not allowed to do a single X operation on these qubits because they would flip this A value. They would actually do something with this A, meaning they would flip the fact that I stabilize this qubit, or in other words, they would flip the stabilizer. So I can look at this really as a stabilizer code now with 3 qubits and a 3-body stabilizer between these 3 qubits. And just from looking at these labels now, I can directly determine which physical operators are actually valid in this code. And in this case, it's each of these Z operators, and which ones are forbidden, which is single-body X operators. And even if I, from here, want to find out an allowed X operator in the stabilizer code, so some kind of operator that does not flip the stabilizer value, well, then I can just try and combine some of these qubits until I don't get this A anymore.
This view on the flow labels really gives a good way to interpret any circuit which has auxiliaries, because we can always put the auxiliaries here. We have, for example, a plus eigenstate auxiliary, and we can just label all the qubits as we've done before. When we are not using CNOTs only, we got mixed labels, and because of that, we need to take both of the labels of the auxiliary qubits, but as we've already seen, one acts trivially. We just mark it with a dot, and the other one is the forbidden operator, and that one we mark with a cross just in order to be sure that we are not using it involuntarily because it destroys our code space. And then we can do the labels just like we were used to. And whenever we come to a rotation, we just read off the corresponding label and we check whether there's a destabilizing label in there. And for instance, if we are looking at the Rx rotation on the first qubit, we get a label 1, 2. That perfectly fine translates into an X1, X2 rotation, and we are fine. And the same is true for the RZ rotation. For the Y rotation, we have to be a little bit careful because we have to combine the two labels, and then both of the crossed out operators cancel out. And this is why we actually can do this operation in this point of time. Afterwards, we want to do the decoding, and there we will see that we really need both of the auxiliary labels, because if we look at this point, then we see that we have the red A in front of the blue A. And this has, the two of them have to be swapped. And if we swap them, of course, we get a minus sign. And this is the case why we need to include this A dot blue operator in there in order to get the phases correct at all times. But after swapping, we can just ease out and decode the whole circuit and then get the information that we are really decoding fully to the original state, to the original trivial labels. Yes, so that's what's come out when we are only using the flow labels, but we can actually add a little bit more of information and get a very efficient way to combine the flow labels with the Clifford tableau, because the Clifford tableau is just the inverse of the flow labels in a sense, and we always can interpret our flow labels in the Clifford sense. For that, the only thing we need to add to the tracking is the so-called stabilizer phases, which also come with an action of the Clifford gates on it. And for instance, you get this little I over here because of the S gate we have having, the C0 acts trivially. And with this information, we can really look not only what is the meaning of the Pauli operator at that point in time and pull it back to the beginning of the circuit, but we can also ask, okay, we have a stabilizer here, namely the X operator, which stabilizes the plus auxiliary, and can ask, okay, what is the evolution of that guy? There's one thing one has to do, that's the swapping of the X and Z labels. Funny in the first place, but it really works out very, very nicely. We just look at this plus initialized auxiliary. And because of the swapping, we look at the third red plus in the Clifford phases. And this is the column we have to look at. And then we look, okay, where does this red A come around? And this is only in this place. And this place is downstairs below the wire. And this translates, because of the swapping, into an X operator. Right here, it looks like, is that even necessary? But if we are looking at a different time step, for instance, on the time step where we have the rotation, then we again look at the third red column of the flow labels, which is this red I over here. And we look, where does the A cross come around? We start under the wires, where we find the X operators in the Clifford meaning, and get the X operators, and then we look over the wires and look which Z operators coming round. And we see that this stabilizer we had in the beginning, which is the stabilizer of the auxiliary qubit, evolves to this operator, or if we simplify it a little bit, we get this XZY stabilizer, which is a nice three-body stabilizer in here. And if we like to, we can also find which logical meanings this X1, Z2, and YA have. This is just the original meaning of the flow labels, and then we get this nice stabilizer over here. Thank you very much for joining us for this video. We hope we could give you a nice glance into the world of parity flow labels. If you're interested in learning more, you can read our recent paper on the topic.
We're looking forward to hearing your thoughts and seeing how the community builds on this formalism.